All right, I'm starting the recording. We are talking about basic principles of the internet. I missed the first part of the lecture, but you'll get the rest of it. You didn't miss a whole lot, just some fun stuff. Okay, so you have human speech, which is this analog signal, and then you have computers, which talk purely in ones and zeros. They found out that you could actually fit a lot of information on a line if it was digital. You could have many, many signals going all at once if it's digital, because you can do crazy things with what's called switching. Where's my, I'm selecting the wrong app here. Okay, so we developed new ways of transmitting data. See, with analog signals, I can have multiple signals at the same time. With digital, I can still only have one. So I come up with a new way of transmitting information and cramming as much data onto a wire as possible by using this principle of packet switching. So if only one person can use the connection at a time, we have to find a way to share that space, share that wire, in a kind of the same way as the operator and the party line, only way faster, like way faster, and with what made way more protections for privacy than a party line had. So what is a packet? A packet is a bundle of bits that a sender wants to send to a receiver. That's all it is. It's actually not very big. I don't even think they're like a megabyte. I think they're very small pieces of information. So I want to send a signal to somebody else, or my computer wants to, more likely. I don't want to send bits. I don't know what bits mean. They're just ones and zeros. I can't read those. So it's like a little sequence of 1 0 0 1 1 0 0. So there's like a packet. To make a packet complete, it also has to have, like, it has to be stamped and addressed. It has to have a return address. It has to have a sender and a receiver. So let's think about some of the different ways that computers will communicate. What's one really big way that computers communicate that we're doing right now? We are video conferencing in real time over the internet.
And then social media too.
Social media, that's primarily text and pictures. It's asynchronous, so it's not in real time, but it's still like a computer sending some information to a server, and then somebody else downloading it later or immediately after, or whatever. So that's a really massive amount of processing that goes into that. So these are some of the different ways that a bunch of computers can all talk to each other. And so a bunch of different ways in which I want to send a packet. Maybe I want to post a picture of my kid on Facebook. I want to talk to you guys on Zoom. The camera's over here. The pictures are over here, but the camera's over here. So if I want to point at you, I got to point there. So how do we do this fairly? How do I say, okay, if only one person can send a packet at a time, and let's talk about this in a very limited sense. Let's say we're all in the same room and we all have our phones and we're all on social media doing that. And we all want to send tweets at the same time or post pictures on Facebook. It is a fact that only one of us can talk to the wireless access point, the router, at once. So in that classroom, only one of us can talk at a time to that computer. But it doesn't feel that way, does it? It feels like we are all just communicating with with Twitter at our own pace. I don't feel a delay. I don't notice any sort of I don't notice that it's anything but real time. And so how are we accomplishing this in a way that's fair, and so that everybody feels like they have an exclusive connection to that wireless access point? And that's where the switching comes in. So I want to send packets. I want to figure out a way to make sure that those packets get there in the safest way. Another question that we need to ask before this is all going to work is how do we do this fairly? And then also, why isn't this working? Push this button, it's supposed to advance the slide. And then the other thing is, how do I make sure that each packet is going to get where it's going? That's the other thing. That's the other aspect of this. Um, so if it's like what if we want to send a lot of data? Why isn't this thing not? Is it this? There we go. What if we want to send a lot of data? So if we want to send like a whole video, like we're talking in real time in a video conferencing app, that's a fairly large amount of data being transmitted really, really rapidly. So, and that's a continuous stream of bits, but it's not getting sent like as a continuous stream of bits. You're not getting like this like unstopped, unceasing stream of bits. You're getting like a little bits and bursts at a time. So what they're doing is they're taking the signal, ripping it apart, and then putting it back together again. So each frame of video that you're getting from this, from my screen share here, right here, is being torn apart, like, and then put back together on the other end. So my computer's taking it apart. It's getting sent across the internet as a bunch of random packets, and then it's getting to your computer, and then it's being put back together. So these are kind of like the big challenges that need to be overcome. We need to do it fairly. We need to make sure every packet gets where it's going, and we need to find a way to take it apart and put it back together again in the same order. And in order to do that, we have to have rules. Does anybody ever see this movie, The Big Lebowski? Anybody? No. John Goodman and what's his name, with Steve Buscemi and Jeff Bridges. It's a great movie. So we need a set of rules. We need a set of rules to govern who gets to access the wireless access point when. We need to make sure that everybody gets to every computer on like my home network, like, because there's so many things connected to my home network. I mean, it is probably it's probably pretty absurd, honestly. Do I know my password? This is my router. I'm sitting at home, so I can see there's 22 clients on my network. And that is like security cameras, and it's like security cameras and a printer. There's a printer. There's my Nintendo Switch, an Amazon Echo. There's so many things here. This is this computer that you guys are talking to. This is my computer. So like there could be tons and tons of devices on any one network at any given time. So we need to have some rules to decide who gets access at what time. And I'm not going to say we don't need to know how those rules happen, but we do need to know that that there are rules that says that we're all going to take turns. And it's going to happen really fast, but sometimes you are not connected and sometimes you are. Sometimes you have right of way and other times you don't. And we do this with a set of rules called protocols. The earliest ones, the ARPANET days, they did not have any security at all. Like nothing is encrypted. Everybody just kind of trusted everybody else to not like listen in and snoop on your packets, which is really easy to do if you have a very simple network. You can just listen to everything that everybody's saying. Now, of course, our protocols are incredibly complex and have built-in encryption, and our connections are all secure. This is the thing that gets me about like government bureaucrats in Congress that are all like, we need to program backdoors into all these protocols so that the government can blah, blah, blah. And I'm like, no, you can't. You can't do that. If you create an insecurity in your network, then the network's insecure. If you create a backdoor, then somebody else is going to find a way to exploit it. We've spent a lot of time trying to get rid of backdoors. So the internet is basically governed by a whole collection of these protocols. So, and there's two that we're going to talk about. The internet protocol. Somebody made this meme. I don't know. I found it randomly and I was like, wow, somebody.
A file to update the prices rather than fucking.
Somebody like literally created this meme about the internet protocol. Its job, they call it IP, the internet protocol, is for addressing and routing. So this is what you were talking about, Billy, about IP addresses. So on my network at home, every computer on my network has an IP address that starts with the same 6 numbers, 192.168.1, and then each one is numbered from there. And I think it just assigns a random number. I'm not really sure. I don't really care either how my router assigns IP addresses. So IP addresses are just like a collection of numbers. And if you look at this section in the text, I think there's even an example that you can follow through. I think it uses the LLTC IP address. It's kind of like the address on an envelope. Everybody's address is kind of more or less static. I mean, they do change, but for the duration of a connection, you're going to have the same IP address for the whole time. You can actually find out, if you open a web browser, you can find out what your IP address is. What's my IP? This is my public IP address. Right there. If you open a command line and ping that number, you'd be pinging my house. Oh, that's my public IP address. And I don't know if this is a shared IP address. I don't think so. Yeah, it might be. It might be shared. I might be sharing this with a bunch of people at Paul Bunyan. Or we have another public-facing IP address somewhere else or something like that. I'm not entirely certain how Paul Bunyan does their IP routing. I might be sharing that connection with a bunch of other people. Because there's only so many IP addresses out there. There's like 4 numbers between 0 and 255, and a bunch of them are reserved anyway. And so I think that like, I don't know, there's only like a couple of billion possible combinations there. So, I mean, think about how many people there are in the world. There's way more people than there are IP addresses and way more devices. So we have to do clever ways to kind of expand that space. And the big thing that we need to do is not have to punch in IP addresses by hand. So the way we've done it now is we've created like a phone directory called the Dynamic Domain Name Service, where we translate domain names like LLTC.edu into an IP address. So that's a whole part of this IP system, is the whole DNS thing, is looking up in a phone book that LLTC.edu translates to this IP address. Because your computer doesn't care about the domain name. The domain name is there for you as a human. In fact, it's a huge inefficiency that's built into the system. If everybody just used IP addresses, we would save ourselves an incredible amount of processing time. And another interesting thing is that when I send a packet across the internet, like you guys are receiving all of the packets that are from this PowerPoint presentation on my computer, they're not following the same route. Like I tear this, each like individual frame of video that you're getting has been torn apart into tiny little pieces and shot across the internet. And they aren't even all going to go in the same direction. They're going to go zipping across in multiple different routes across the internet. And those like and presumably they'll all get there, but they'll all follow different routes. They'll all take different roads, and this is built into the system to prevent congestion, so that they're going to zip from node to node across the internet in different ways. We currently have 2 versions of the Internet Protocol in service, version 4 and version 6. I don't know why they're numbered this way. I don't know why there's not a version 5, but this is just how it is. Version 4 is what most people use. Pretty sure Paul Bunyan, I'm not sure about Midco or Arvig, but Paul Bunyan does not use version 6 yet. I think they're ramping up to roll it out, but they're really dragging their feet on the deal. But version 4 is out. Like there are no more IP addresses to hand out. So they're doing all sorts of like clever things to kind of, create subnets so that you can still use IPv4 when we all should be just slowly moving our way. We all are slowly moving our way to version 6, and sometime in the future we will we'll all be transitioned, and that rollout will be complete. But it's been going on for like 10 years, so it's going to be a while. So yeah, the Internet Protocol is the protocol that's designed for addressing and making sure that packets get where they are going. The other big protocol that the Internet has is the Transmission Control Protocol, TCP. This one right here. Let's see, where's my pen? I have a pen. Yeah, there it is. Oh, that's my laser pointer. Pen. TCP. We'll talk. I'll briefly mention UDP because I thought this meme was really funny. So the Transmission Control Protocol's job is taking a message. I have a picture that I'm trying to send across the internet, a picture of my cat or whatever. And TCP is built into your computer system. It takes the message, breaks it apart into tiny little pieces, and then hands them off to the IP protocol, which fires them across the internet. And then at the other end, they also have a TCP protocol built into their system. Will collect all the pieces as they come in, and once they have them all, put them back together, presumably in the right order. And which isn't that hard. I mean, they just like each one is like 1 of a billion, 2 of a billion, 5 of a billion. I don't know how many packets. I think a picture would probably break up into, I don't know, maybe a couple hundred packets. The other thing that TCP does is it makes sure to acknowledge every single packet. This picture right here is kind of an example of how TCP works. It's a very careful handing off of everything, making sure that the data gets there intact and undamaged and everything is there. There's another protocol called UDP, the User Datagram Protocol, which is what Netflix uses because it's fast, where it's just a fire and forget thing. It's just like we're taking our data, just chucking it, and hopefully it gets. Hopefully most of them will get where they're going, and that's kind of how Netflix works. And that's better for like video streaming. And that's probably what Zoom uses too. TCP is designed to make sure that every single packet gets there. And if it doesn't, we will resend it. We will make sure that every packet gets there. And so there's a fairly strong guarantee that all the data will get through using TCP. Transmission Control Protocol. Another interesting thing that it does is congestion control. So if it'll time the timing between every acknowledgement and see how long it takes for each acknowledgement to come back, and it'll get an average. And if it seems like it's taking too long, it'll actually back off and stop sending quite so many packets quite so quickly. So built into the TCP protocol is this thing where everybody plays nice. I won't send as many packets if the network seems like it's getting kind of slow. You could totally program your own TCP algorithm that doesn't back off and just keeps sending protocols. And that'll cause everybody else to back off, and you'll get like this exclusive and super fast internet connection. This is an interesting theory because they call it the TCP tragedy of the commons. And the thing that's weird about it is nobody actually does it. Nobody doesn't play nice. Everybody plays nice, and we're not really sure why. Maybe it's just because it's hard to do. Because it is. TCP is a pain in the butt to implement. I partially implemented TCP for my networking class, and it was a semester-long project. It was horrible. Yeah, and like I said, there are other protocols at this layer, like UDP, which is fire and forget. We're just going to send our data. We're not going to acknowledge anything. We're just going to assume that in a low latency, fairly reliable network that most of the packets are going to get there, because it doesn't matter if you're watching, some movie on Netflix that if you miss a packet, it's not the end of the world. You're not even going to notice it. So if 99% of the packets are getting there, everything's good. So those are the two main protocols, the IP and the TCP, that govern the internet. Then we have this other thing called the World Wide Web. I think this is actually on the quiz for this module. The World Wide Web is was invented in 1990. But so the internet became a thing. Like people actually started getting internet in their homes in like the 80s. I didn't. It's not me, but some people were. Rich people maybe, or I don't know, really really tech oriented people. You could get internet access. You could actually you could like do dial up. There was dial up where you could take your phone, you actually dial a phone number, and then you put the phone on the modem, and then it would send squeals and beeps and stuff, and that would actually be your internet connection. When I was a kid in middle school, so this must have been like early 90s, I actually had some friends. So this is like sixth grade, seventh grade probably. I had some friends in middle school, and we used to dial into this chat service. It was seriously like some guy had a server in his house you could dial up to and just chat. Like it was just a chat window using a really simple protocol and a phone line. And so I would actually do this, and we would just sit for hours just chatting about dumb, stupid stuff. It was a wild time. It was like I can't remember. I think they called it Simon, and that's all we did. Is we just, I mean, you can't pass pictures; it's all text. So I know it's kind of fun. And that's something that doesn't exist anymore. Nobody does that. It was a very brief window where that was a thing. But like, okay, so what happened was the internet is this thing, but it's this really clunky text-based. It's all these like message boards, and it's not intuitive to use, and you basically have to type in things like, you have to type, like, know somebody's IP address to contact them. And along came Tim Berners-Lee, and he's like, there's got to be a better way to do this. We've got to simplify this, the way that people interact with the internet. And so he came up with a series of technologies, a whole system of interrelated technologies that all work together, called the World Wide Web. Are we over time? We are, aren't we? We'll pick this up on Friday.
Alrighty, man, you're just rolling.
It won't be like this all the time. We'll just do work. Next week will be kind of a work week.
Okay, so we are meeting Friday?
Yes. Stop the cloud recording. Yes.